In the lesson today, we are going to look at laws of logarithms. We've seen previously that logarithms and exponents are inverse operations to each other. Therefore, it might be a good idea to pause and look back to revise the laws of indices. So today we are going to extend these laws of indices, connect the new learning with the previous one, and we are going to deduce and use the laws of logarithms. At the end, you'll need to know how to use the laws of logarithms. However, in math, everything is related and no formulae come from nowhere. That's why we're going to deduce them to see how they appear in mathematics. Let's start with a short recap from last lesson. Please pause the movie and try those questions. Of course, you can use your calculator, but to understand these types of questions that you see here on the board are to be done without calculator. Please pause the movie and try them. Okay, hopefully you got 2. 6 to the power of 2 is 36. Negative 1, because 6 to the power of negative 1 is 1 over 6. 6 to the power of 0 is 1, so the answer here is 0. 10 to the power of minus 1 is, as you know, 1 over 10, so is 0.1. So the answer here is minus 1, and the answer here is negative 2, because 10 to the power of negative 2 is 1 over 10 squared, so it's 0.01. Okay, it is good to remember that exponents and logarithms are inverse to each other. So the equation y equals b to the power of x, it's equivalent with x is log in the base b of y. Remember, b to the power of x is y. And this works for any x real and for any y bigger than 0. So y needs to be bigger than 0 because b to any power gives me a positive number, so y cannot be negative. Here we start having the domain of the function logarithms. The domain is y bigger than 0. Remember from last lesson when we drew the graph, and that is going to be, for example, the graph of log in the base 2 of x. X is positive. Here you can't draw anything. X is positive and y is any real number in this definition of the function. Now, other properties are log in the base b of 1 is 0. Log in any base of 1 is 0 because any number to the power of 0 is 1. Log in the base b of b is 1, where b is any base, because b to the power of 1 is b. Log in the base b of b to the power of n is n, because b to the power of n is n. We are going to have 3 properties that I'm going to prove in a moment. So here they are. Log of x times y is log x plus log y. And when I don't choose a base, it means that it's any base for this formula. So I don't want to write log in the base a of x, log in the base where a is any positive real number, which is not 1. Remember the definition of the base. The second one will be log of x over y is log of x minus log of y. And this again works for any base. And the third one is log in the base a of x to the power of n is n log in the base a of x for any a as the one before and for any n which is a real number. So these results are true for logs in any base. Now, on the next pages, I'm going to prove each of those results. The proofs are not in your syllabus, but it's nice to see how they connect to the laws of indices that we learned before. Following the proofs will help you understand better. However, if we don't want to follow the proofs, you can stop the movie and go to the next learning experience from your Google Classroom. Let us now prove the first law of logarithms. Log in the base a of xy is log in the base x plus log in the base of y, where a is bigger than 0 and not 1. Always that's the definition of the base, the domain of the base, and x and y need both to be positive because that's a domain of logarithms. How are we going to prove it? So, as we mentioned, each law of logarithms is related to a law of exponents. This is a reason why it might be a good idea to move from logarithms to exponents to use what we know. So I will say let log in the base a of x, y be p, log in the base a of x be q, and log in the base a of y be s. Therefore, we can write that a to the power of p is xy, a to the power of q is x, and a to the power of s is y. So, in the first law, I'm going to look at the right-hand side. And the right-hand side tells me to add q and s. So, if I'm looking at the last two rows, I see that xy is a to the power of q times a to the power of s. And here is when the law of exponent comes. And that's a to the power of q plus s. As we see from relation number 1, xy is at the same time a to the power of p. Therefore, q plus s is p. Remember that q was that one, p was that, s was that term. So q plus s is p. So we proved the first law of logarithms. On the next two pages, I'm going to prove the next two ones, but my advice is to stop and try similar proofs by yourself for the next ones. Here is the second proof, very similar to the first one. Just at this point, I used another law of indices. Here is a proof of the third rule, and I use another law of indices where a to the power of q to the power of n is a to the power of nq to prove that n times q, that was q, is the same as p, and that was denoted by p.